Thanks very much, and I want to thank the organizers for putting this great conference together. I've really been enjoying it, and really appreciate the opportunity to speak here. Like many people have expressed, I kind of don't know why I'm here at this conference on surface bundles, because I feel like I don't really do anything about surface bundles. I really do more things about geometric group theory and group extensions and so on. But I realized maybe what ties us all here together, if we're not all doing surface bundles, is hopefully we all love surface bundles. You down at Mark. So what I want to talk about is some work that I've done about free-by-cyclic groups, but really it's all motivated by some beautiful theory about fibered free manifolds. So I thought what I'd do is begin to spend maybe the first part of the talk sort of reviewing this theory of fibered free manifolds and what it gives you, and then talk about how maybe you could push that farther beyond the world of manifolds and surface bundles to prove other things. And this project is a joint project with Ilya Kupovich and Chris Leininger. Okay, so yeah, so let's just first begin here. Let's say sigma will be a surface. Closed genus G, at least 2, surfaced. And let's take a homeomorphism. Of the surface, and then of course from this we could build the mapping torus, which I'll just call M. And the mapping torus comes equipped with a map to the circle, and it is in fact a surface bundle, right? So it's a surface bundle over the circle with fiber your surface sigma. Okay, so this is the thing I want to talk about for the first part of the talk here. And let me just call this map, maybe I'll call it sigma, okay, for the fibration. Okay, so here is one really beautiful fact that about these manifolds that I like a lot, is that if you look at the dimension of the first cohomology of every manifold, and if it's at least 2, so bigger than 1, then I have this fibration of M, but just this fact, together with the fact that I have a fibration, gives me infinitely many fibrations. Okay? So then M fibers in infinitely many ways. Okay, so I think most people are probably familiar with this fact, but in case not, or if you forgot why it's true, I just wanted to explain really easily, basic, how you get these infinitely many fibrations. Okay? So how do you do it? All right, so let's let omega be the pullback under sigma of the volume form on the circle. So this is -1 d theta. I pull it back, and this is a closed, nowhere vanishing one form on my manifold M. Okay? So basic thing is if I have these properties are this property of nowhere vanishing is an open property. So I could take this form and perturb it a little bit, and I'll get new forms that are still nowhere vanishing. Okay? So that's the whole basic point. So there's a neighborhood in the cohomology of this cohomology class represented by omega with the following property. Let me even draw a little picture here. So here is omega, and I'm drawing this neighborhood U, open neighborhood around it, and it has the following property. So if I take a class, I want to call it omega prime, and I want to take this neighborhood and scale it by positive things so that I can have an integral class. Okay, you know, maybe this is probably a small neighborhood, so maybe there's no other lattice points in it, but I'll scale it, take the cone on it, and out here I'll find some other thing, projectively, in this neighborhood. And since omega was nowhere vanishing, I can choose this neighborhood so that this omega prime will also be nowhere vanishing. So this is nowhere vanishing. Oh, sorry. Each omega can be represented by class in here, nowhere vanishing closed one form. Okay, so I'm going to perturb this closed one form, get a little neighborhood in the cohomology with this property that everything in there can be also represented by a closed nowhere vanishing one form. Okay, so then I could do the following thing. Integrate along paths. Integrate omega prime along paths. What do I mean? You just take, maybe fix a base point inside of M. Maybe here, this is M. I fix a base point. You have some other point P. I just take a path from my base point to P, and I integrate that path along omega prime. That gives me a number for that path. But if I chose a different path, it's not a well-defined number, right? Because I have to choose a path. But if I choose a different path, the fact that I have an integral cohomology class says those numbers differ by an integer. Okay? So what I get is a map to the circle. Okay? And that map will be a fibration. Okay? So I'll call that fibration sigma prime. And it'll have a different fiber, you know, who knows? Okay. Does that make sense? So I just used this fact that I have positive dimension to produce in here, you know, there's infinitely many such classes, integral classes in this code. And I now have infinitely many different vibrations.
I think this needs to be credited to a.
Oh,
There is an easy thing, but
it's an easier thing.
but it's not like the deepest. But Thurston,
I
think
think
it's a huge.
I think even
conceptual
before Thurston, it's like
Well, there's Tischler has
Tischler had
the
this
infinitely many
unit.
vibrations.
Yeah, that's
Yeah.
true.
That was Tischler.
Oh, okay. But that still makes great observation.
It's a great observation. Yeah. Okay. So you might wonder, you know, what's the fiber here? How can I figure out what the fiber is? You know, well, what's its topology, what's its genus, and so on. So I can also tell you simply how to figure that out. Okay, so let's. I have this two-plane bundle. The kernel of my original fibration, sigma. So I could take the derivative map for sigma. Its kernel is a two-plane bundle over my manifold. And this has an Euler class. E in cohomology, my manifold. And the Euler characteristic of my original fiber is just the integral. I just integrate this Euler class over that fiber. Okay, so the Euler characteristic here of my original fiber is just the pairing of that fiber is a homology class. I pair it with the Euler class, and that's the Euler. Okay, so now
in this theorem, do you require that the fibers are connected?
no, I don't.
Because if you don't, then it's not so a great result anymore, right? Because then if you sort of, you can map the circle, consider it as a covering of another circle, and then.
That's right. So the things you're talking about are all on this ray.
Right.
If I just multiply that, it corresponds to going out by array. That's taking multiple copies of my fibration. But this is an open cover. I mean, this is an open neighborhood in a two-dimensional thing. So there's also.
No, I understand
things.
that, but it does not is not reflected by the statement of the that you make.
Or you have like a primitive classes?
No, the fibers move in many ways, but it's
You want
even with the
primitive
connected
classes?
fiber.
Even with connected fibers.
Yeah.
So you can show
Well,
that
I
if you take.
understand that, but how do you put that in the statement of the result? I mean, that you don't have these rather trivial examples.
So yeah, you can show, kind of not too difficultly, that if you take a class like this and you choose a primitive representative, so you scale it so that, you know, it's a primitive vector, then the fiber will be connected.
Okay.
Yeah, you can, that's not too hard to show. Okay. All right, so this is the Euler characteristic of this fiber, and you might wonder, what's the Euler characteristic of the other fiber? Well, I could calculate that in the exact same way. I could take the two-plane bundle for this fibration, use its Euler class, and pair it with this fiber. But the important thing to notice here is, how did I get from one fibration to the other? I just perturbed my one form a little bit. And this two-plane bundle, it's the same thing as the kernel of omega, of that one form, and that bundle is homotopic to the kernel of this other one form. They're just a perturbation of each other. So that says the Euler class for this two-plane bundle is the same Euler class as for the original one. Okay? So the Euler characteristic of the other fiber is also given by just pairing that fiber with the same Euler class. Okay, so what that says is that calculating the Euler class of the fiber for the things in here is a linear function. Okay, so on this cone. And I should say Euler characteristic of the fiber. Okay, makes sense. So that's very nice. We see that your manifold fibers in infinitely many ways, and you can calculate the Euler characteristic of different fibers using this linearity. And this in fact shows that you fiber with arbitrarily large genus, right? This linearity of the Euler characteristic and so on, which is already it's already a nice observation. So now I want to talk about how to organize kind of all the different fibrations together, and that's done by the theory of the Thurston norm. Okay, so this is from paper Thurston from '86, and it proceeds as follows. So if I have a homology class, my manifold, let me define a norm, or just something, to be the following. So it will be the infimum of this kind of modified Euler characteristic, where S is a surface representing alpha. Okay, so you pick a homology class.
You didn't tell us what the modified Euler characteristic.
I'll tell you in a second. Yeah. So you pick a homology class here. You represent it by embedded surfaces in your manifold, and you calculate this number. This number is just, throw out the S2 components of your surface. So you have this surface representing this homology class. You throw out the sphere components, and you calculate the Euler characteristic of what's left. Add up the Euler characteristic of those components. You get a number. You take the infimum over all possible ways to do that, and that's
Minus sign.
huh?
Minus sign.
Oh, minus sign. Thank you. Minus sign.
You throw out it.
The hat says do the Euler characteristic and throw out those components.
So Rigor, it's important that these are not necessarily connected surfaces.
They're not necessarily connected surfaces. Okay, so this is a way to get a number assigned to any homology class like this. And some observations. First of all, that it scales nicely. And this you can see by, if you have surface realizing this infimum for alpha and you want to realize k alpha, you just take k copies, take k parallel copies of it and so on. Okay? And then another observation is if S is a fiber, okay, so like in this situation over here, I might have had that surface sigma, then for
Sorry, is it fiber of some vibration?
is a fiber of some vibration, yeah, that's what I mean by a fiber of some vibration, then the norm of its class is just the Euler characteristic, and minus Euler characteristic of the fiber itself. So fibers realize this in field. That's what I'm saying. Okay? So, and Thurston proved that this function extends.
I think you misspelled Thurston, dude.
Thank you.
Still. Grandfather.
This function extends to a norm on H2. Okay. Extends by, use this fact to define it on all rational points by homogeneity, and then it's defined in a dense set of points, and that extends continuously to some function, and that function will be a norm. Okay? Or a semi-norm. Semi-norm. Okay, so some things could be 0. Okay, so I could dualize on the first by Poincare duality to get a norm. Oh, I should use real coefficients here from this vector space. Okay, so I have a dual norm on the first cohomology, which are the things that parameterize, we sort of saw here that cohomology classes were giving me fibrations. And, okay, so let's just take this and combine it with the things we were just thinking about a second ago. So, in this situation, I'm here at this fibered class, and the norm, I know, is for things, so for integral points over this cone, the norm is given by the Euler characteristic of the fiber. Okay? And we saw the Euler characteristic of the fiber was a linear function. So that means the norm is linear on here. Okay, which means if I look at the unit norm ball, the unit ball for the norm, it's going to be, linear. There, it's going to have a flat face. Okay, does that make sense? So in fact, what Thurston showed is that the unit ball of, we'll call it B star, of this norm on the cohomology is a finite-sided.
So is the hypothesis here that M admits a fibering? Or?
I guess here, no. I mean, he proved this even if it's not fibered. The unit ball is a finite-sided polyhedron. Okay, so we saw here that, in the case of a fibration, you see some kind of linearity, but in fact, the whole unit ball is a polyhedron. And it turns out to be the case that every fibered class, by this observation, has to live in the interior over a top-dimensional face. Has to live, over a face. Lives over the interior of a top-dimensional face.
So doesn't semi-norm not allow the possibility that it is 0 in certain cases? So
That is possible.
yeah. So what is then the unit ball?
So in that case, I guess the unit ball is some infinite thing.
Not a finite-sided.
Well, that's finally many sides.
Finally, many sides, but some sides could be infinite.
If you want to get rid of all of these things, it's a norm.
It's a norm if your manifold's a hyperbolic manifold.
It doesn't contain a torus, right? The principal torus.
Yeah. Okay.
Okay. So the fibered classes, each fibered class has to live in the interior of a top-dimensional face, and Thurston proved that, moreover, everything in the cone over a face like this is fibered. Okay? So, and every integral class and the cone on such a face is fibered.
Such a face means containing.
Yeah, that's right. Yeah, not every face. Okay, so we already kind of saw that being fibered is an open set, is open condition, and Thurston proved that you can kind of extend this argument over a whole face of the norm ball, basically. So in fact, the fibered classes, you know, the different fiberings are organized as follows. Let me just draw a picture. So here is H1, there's this unit norm ball. Maybe it looks like the stop sign, and some of the faces are special. They're called the fibered faces. They're the ones that contain fibers, so maybe it's, you know, this face, and this face, and that face, and that face, for example. And then if I take the cones on these faces, all of the integral points over such faces correspond to fibrations, and all the other integral points don't. Okay? So the Thurston norm exactly tells you which homology classes corresponds to fibrations, and so on. So it just organizes all of them. Okay. So now I want to stop looking at this from such a topological perspective and now take just very briefly an algebraic perspective. So if I have so the algebraic perspective, I'm going to sort of comes from the fact that cohomology is the same thing as homomorphisms from a fundamental group to Z. Okay. And if I have a cohomology class, I could look at the corresponding homomorphism to Z, and alpha corresponds to a fiber. If and only if the kernel of alpha from this map, use of notation here, kernel of that homomorphism is finally generated. Okay. In the case that it is a fiber, the kernel is just the kernel is the fundamental group of the fiber. For alpha. In the case that it's fibered, and one can show that if the kernel is finally generated, then in fact it has to come from fibration. Okay. So being fibered just corresponds to finite generation of the kernels here. Okay, now I want to give you some other more abstract algebraic definition, algebraic characterization here. So this is equivalent to, in this case, alpha lying in what's called the B and S invariant of fundamental group manifold. Okay, so. Question?
BNS means
Thank you. Vieri, Neumann, Strabel. They define this invariant for finally generated groups. Let me, as an aside, just tell you the definition. So G finally generated, then this invariant is the following thing. It is the set of homomorphisms, and I'll find it this way. So I look at homomorphisms to R, and you're in this invariant if the following thing holds. So I'm just going to write it down, and you can sort of tune out if you want, and ignore it forever. But that's it. Anyway. So if the commutator subgroup is finally generated over a finally generated submonoid of the set of things in G where that are positive or non-negative. Okay. All right, that's something you can define. All right. So we're not going to use this definition, but the point is, the group acts on the commutator subgroup by conjugation. So I want it to be finally generated as over a submonoid of the positive things. That's what it is. Anyway, so that's, the definition's not so important, but this completely algebraically defined thing, in this case of your fiber 3 manifold group, corresponds to being a fibration. All right.
Sorry, you mean like in hom of G comma R, you ask sort of which figures of the fibration.
That's right. That's right. You could just turn off your topology, you could take off your topology hat and just look in hom. You can just look in here and say, well, what homomorphisms correspond to fibrations? Well, it's this. Okay? It's algebraically defined. Okay. So one other thing I want to say about these different fibrations of your manifold. Okay, so we've seen that your manifold might fiber in lots of different ways, and for each one, you get a monodromy. The monodromy of this bundle, which in this case, the monodromy is a map from the fundamental group of the circle into the mapping class group of the fiber, so that's just given by an element. Okay, so that's just some mapping class group, mapping class of the fiber. And you could ask the following question. How are the different monodromies related to each other? Okay, does that make sense? Right, I have this one manifold. I take two different fibrations of each other, of it. You know, what could I? If I know one, what could I say about the other, and so on. So the first thing you could say, well, Thurston showed that M is a hyperbolic manifold if and only if our mapping class that we used to build it is pseudo-Nassau. Okay. So just some property of this homomorphism gives you something about the geometry of this manifold. And since this is an if and only if, it tells you that the same thing holds for all monodromies. If one monodromy is pseudo-Nassau, they're all pseudo-Nassau. So that's already an amazing fact. Okay, an amazing relationship between the different monodromies, the different fibrations.
Is there a way, do you think there's a way to see that without going through this?
I don't know.
Well, if you're not pseudo-Nassau, you have some reducible curve, which will give you a, maybe, I guess.
One direction is easy.
Yes,
Yeah.
yes.
One direction.
Right now,
One direction is easy. But the other direction is, I don't know.
right, that's the thing.
I mean,
The other direction is.
the other direction is
I'll
harder.
about the whole thing.
and I think you need to use that to know that all monodromies are pseudo-Nassau. Oh. Okay, so now that we know this fact, you could start to ask yourselves, oh, what about information about these pseudo-Nassau? So one of the most important invariants of a pseudo-Nassau is called its dilatation. Okay, so the function, I could now define the following function for alpha, a cohomology class, a fiber cohomology class. I set h of alpha equal to the logarithm of the dilatation of the pseudo-Nassau. So a pseudo-Nassau, again, leaves invariant some foliations on the surface, and it scales them by lambda and 1 over lambda, and this lambda is called the dilatation. There's some important number associated here. Pseudo-Nassau, and so now, using all this, I could define this function on the integral classes. Okay? This is a perfectly well-defined thing, and it's homogeneous in the sense that h of k alpha is 1 over k h of alpha. So I've now defined it in a bunch of integral classes. I can extend by homogeneity to all of the rational classes. Then it's defined in a dense set of points. And you might wonder, could I extend it continuously? And in fact, you can. And this is due to Freed. So you can do that, and also McMullen sort of improved on that and expanded it a bit. But h extends to a convex, continuous, and in fact, better than continuous, real analytic function for each fibered face. Okay. So the picture now is I have these different fibered faces of my Thurston norm ball. For each one I have a cone, I have a bunch of integral points in there, and I could ask about how this function behaves, and it behaves very nicely. It's this real analytic convex function. So that's saying something like the monodromies are related to each other via their dynamics.
And that, like, log of lambda is the entropy, just since you said the word dynamics.
Yeah, this is the entropy of this homeomorphism, of the pseudonasa. Okay, so that's, right, there you go. That's the review of the fibered face theory for fibered hyperbolic free manifolds. And now I want to go a different direction. And the different direction just comes from the following simple observation is here we started with a closed surface. We had a closed surface and we had this nice closed three manifold. What if we took a punctured surface? Okay, so what if you know, this sigma is a punctured surface? Okay, so then I still have this picture, and it gives me a short exact sequence. Coming from the on the fundamental group, and this gives me a way to split my fundamental group as follows, as a semi-direct product of this fundamental group of the surface with Z, where here V is F star, which is in out of the fundamental group of the surface, and now the fundamental group of the surface is a free group. Okay? It's a punctured surface, so its fundamental group is a free group. Okay, so now what I have is a free-bicyclic group, and if you think about it, I mean, this whole theory still works for these groups. Okay, so this is giving me sort of telling me about different ways to split my free-bicyclic group as a free-bicyclic group. All the different vibrations will give me ways to give me different splittings of this. And I have this nice, beautiful theory for all the different splittings of this group. Okay? But this is a very special kind of free bicyclic group. Namely, the automorphism I used came from a surface homeomorphism. That's a very strong restriction on a free group automorphism, that it came from a surface. Okay? So this is restrictive. There's many, many more automorphisms of free groups that don't come from surfaces. So what I want to do is expand this picture and now to erase this restriction and see what can you say for other free group automorphisms. Okay, so what about for arbitrary? So by which I mean non-geometric. Non-geometric, I mean not coming from a surface. Things in out Fn. Automorphisms of free groups. Okay. All right, so there's not a whole lot of time left, but let me just kind of give you the setup and try to say what some of our results are. So here's the setup. Let's now fix some automorphism. Okay, and I said arbitrary, but really I want to put some restrictions on this. So let's fix an automorphism, and there's three here, and suppose that phi is represented by what's called an expanding irreducible train track map, which I don't want to define. Okay? Well, what it is, it's just a graph map. So gamma is a graph. The fundamental group I'm identifying with my free group. And you should think of these conditions are like an analog of a pseudo-Nassau homeomorphism of a surface. Okay, so now it's some kind of graph map that has dynamics kind of similar to a pseudo-Nassau. Okay, but it maybe doesn't come from a surface. Okay, so that's the assumption I want to make. Okay. So then I could build G to be this semi-direct product, free-by-cyclic group. And I'm interested in different splittings of this group. Okay, so how do I understand different splittings? Just like before, they were parameterized by cohomology classes. Cohomology classes are the same thing as homomorphisms to Z. Okay, so I want to look at homomorphisms to Z. And if I have one, it gives me a short exact sequence. So, let me assume it's surjective map to Z, for example. Then it has a kernel and fits into a short exact sequence like that. And it's been mentioned before that anytime you have a short exact sequence, it gives a map from this group to the outer automorphism group of this group. Okay, which is just take the generator here, lift it, that acts by conjugation on this group, which is well-defined outer automorphism. Okay, so that also gives me a monodromy. And out of whatever this kernel is. Okay? And I'm interested in fibrations. What does that mean? Well, that's why I went through this whole algebraic setup here, is because this is what I want to use as fibration, is to be in the BNS invariant. Okay? So that will be the analog. So U corresponds to a fibration. Let's say if it's in BNS invariant of this group.
Alpha. You use alpha?
I switched to U. Is that yeah? I don't know why I switched.
I just missed that.
Yeah. So now this is U here. Sorry.
In this case, is this the same as the kernel being finally generated?
It's not the same. It's more general. It's a weakening of the kernel being finally generated. So let me get to that. So this is equivalent to the following thing. If you don't like this definition, which it's hard to parse, I understand. So being in the BNS invariant here is equivalent to there existing some element that's positive, so a particular positive element, and a subgroup of the kernel that's finally generated, and invariant under this automorphism with the property that these two things generate your group. Okay, so if you like, in this case, being in the BNS invariant corresponds to finding a finally generated subgroup of the kernel. It's invariant under the monodromy and one other element that together generate the whole thing. Okay, so that's what BNS invariant means in this case. And to answer Andy's question, so here, kernel of U being finally generated corresponds to both U and the opposite of U being in the BNS invariant. Okay. In the case of a manifold, the BNS invariant is symmetric, so being in turns out to be the same as U and U inverse being. Okay.
B sub U need to be free, or it's free?
It turns out it's free. Yeah, in this case it has to be free. Okay, so that'll be a finally generated free group that's preserved by this monodromy.
But does the kernel have to be free?
The kernel also has to be free, but it might be infinitely generated. But in the case, anyway, in the case that the kernel is finally generated, it'll be a free group. Okay, so All right, so now we have this idea of what being fibered means, and we also are interested in relating the different fibrations to each other. Okay, so one way you could relate them over there was with this dynamics, this dilatation of the pseudo-Nosovs. There's an analogous thing you could define here. Okay, so the finite BU being finitely generated lets you define the following thing. Okay? So I'll call it lambda of u is basically the stretch factor of my monodromy restricted to this finally generated subgroup. So this will now be some injective endomorphism of this free group, and by the stretch factor, I just mean, I don't want to write it down, but it's just you take an element in B and you apply your endomorphism to the n times, and you measure its word length, and you take the nth root of that. Okay, so it's some like measuring exponential growth, how fast word lengths are growing in this group. Okay, measure with respect.
This BN is not unique, right? You can find different BNs.
Yeah, that's a very good point. This B is not unique, but it turns out this number is well defined, no matter what B you choose. That's not so hard to see, actually. Yeah, but this turns out to be a well-defined number for things in the B and S invariant. Thank you. Okay, so you can check that, again, it's some sort of homogeneity property. So I'm maybe only defined in this case where I'm in surjection onto Z, but I have this homogeneity property so that I could extend it again to all rational classes. So I'll call that this function from Q, B, and S, G, R. Okay, by this I just mean rational points that are in the B and S invariant, or can be scaled. Yeah. Okay, so now I want to understand different splittings of my free-by-cyclic group that has something to do with wanting to know what the B and S invariant is, and I want to know how this function behaves on the B and S invariant. Okay, that's the goal. Right, so the goal would be, if we wanted to have a similar kind of theory, is what is this invariant? It's a hard to calculate invariant in general. I actually don't know how to calculate it. And what is this function? Those two questions. Okay. So, in the interest of time, how about I just tell you what I know? What can we say about this? And then it'll be a mystery, and you can ask me
So you
later.
have 10 seconds left?
I have 2 minutes.
No, to tell what you know.
I see. I should go. I'll just explain how the proof first, and then I'll state the theorem.
Such a lovely advisor.
I just tune them out. To all you younger students out there. Okay. All right, so what can we say? So again, this is with Oberwolfach and Leininger. Okay, so in this setup, the component of this B and S invariant G containing. So I wrote my group as a free-by-cyclic group. So it came with a sort of preferred map to Z, where I just quotient out by the kernel. Okay, so that's some point in the homology. So that's some homomorphism to Z. And I could ask for, I already know it's in the B and S invariant because the kernel's finally generated. So I could ask for the component of the B and S invariant that contains that. And what it is a finite-sided polyhedral cone, convex. Okay, so the component of the B and S invariant is some nice cone inside of there.
Does that be compact? Or
So it's a cone. So by cone I mean
code over something compact?
it's R plus invariant. It's the cone on a compact thing. Yeah,
But-
sure.
So you have like a rational vertices for the.
It's rationally defined, yeah, it's rationally defined polyhedron cone. It's cut out by finally many rationally defined hyperplanes. Okay, okay, that's one thing. Each integral thing in this cone, so that has a splitting. So if you're in the BNS invariant, you have this setup, and in fact, you're an H and, that gives you an H and N splitting of your group as follows. Okay? So if you're in the BNS invariant, you can write your group in this way, and you get this automorphism. So then this automorphism, or endomorphism, U has, again, an expanding irreducible train track representative. Okay. So I'll call that F sub U from gamma U to gamma U. So this is some similarity between the different monodromies. So we started with some assumption, this technical assumption expanding irreducible train track map, saying the other splittings also have representatives with that nice property. Okay? And the assignment this sort of function extends to, again, a convex real analytic homogeneous function H on this cone to R. Okay, so this algebraically defined stretch factor function on this cone, component of the BNS invariant has a real analytic extension.
But you don't want the closed cone, you want the open.
Yeah, the open cone. Yeah, it's an open cone. Thank you. Okay, and then just one more fact I'll just write down, that if phi is something called atoroidal plus fully irreducible, so you should just think that's some free group analog of being Suter-Nassau. Okay, so if your free group automorphs and have these nice properties, then it's also true that each one of these things also is for you in this cone, this integral points in that cone. Okay, so that's some other relationship between the monodromies of different splits.
So what have you written there? If phi is what?
Atoroidal and fully irreducible.
Can I ask you, can you say anything about the other fiber faces?
Oh, yeah. So it's a
I
good
guess you'd
question.
be able to prove
So
that
this is
theorem
like-
without Thurston's.
So this is like a local theorem. It's like you have one point and it tells you the component of the BNS invariant around the point. And I don't know anything about the rest of the BNS invariant. So there's like the weird thing here is, you know, in the three-manifold case, you have the Thurston norm, and you know what it is, and then you can prove stuff about each face. And here we don't have the Thurston norm. Like we're just picking out one component at a time, and we can say some stuff about it. But there's no, I don't know what a Thurston norm is in this case for Freebycyclic. So that's a question. I would, you know, if you know the answer, you should tell me and tell someone. He's like, is there a Thurston norm in this setting that would have, again, a polyhedral norm ball with finally many faces that sort of cones on some of the faces would give you the BNS. So then you could have maybe a much better picture of the situation. I want to stop there. Thank you.
So questions for Spencer?
How can you prove that the function is real analytic?
Well, the function, it's because the function comes from some kind of polynomial.
It's a constant. It's a constant. It is real.
I mean, yeah, maybe the function, there's some sort of polynomial in this group ring. So, I mean, how we prove this is we find some kind of polynomial like this, and by specializing this in different cohomology classes, lets you calculate this function. And since it's like, you know, coming from doing something simple to a polynomial, you can show it varies real analytic.
But you're not saying it's piecewise polynomial, right?
The function, no.
No.
Yeah, I mean, it's sort of, it's defined somehow in terms of this polynomial, but I took a logarithm, and so,
Okay.
yeah, it's some real analytic thing. Yeah.
Greater first.
So if n is a fibered knot, how is this the same? I mean, how is this the same as the previous story, or is it?
That is the same as the previous story. So if it's a fiber knot, then the, oh,
Yeah. Fiber link is probably more interesting.
Fibered link. Sorry, fibered link.
but in that case, it is a three-manifold group, and so the three-manifold theory applies.
So this BNS is the same as the first one?
That's right. It's the same on the cone on the fibered faces of the Thurston normal. That's right. So we were working in this situation, in this sort of
I mean, this component of the BNS or just the whole BNS?
Well, yeah, this component will be the cone on the fibered face corresponding to your fibrate. Does that make sense? So,
But the whole BNS is maybe different?
has many components. Yeah, in general, the whole BNS invariant would have many, in the three-manifold case, it has finally many components.
It coincides with the Thurston normal, right?
Well, it corresponds with the cones on the fibered faces of the Thurston normal. That's what the BNS invariant is in that case.
Andy?
Yeah, so I was trying to imagine how you prove the, I guess this things that all the monodromies either are, have these train track representatives or toroidal ones. So I guess in one of those cases, the group itself is hyperbolic, right?
That's right.
It's the second one. How do you do the first one then?
Okay, so the atoroidal, that's right, so that's really not our theorem, that's someone else's theorem, that because the group is a hyperbolic group.
Right.
So the other one is sort of more subtle,
Yeah.
and you have to use the fact, I mean, basically we build a nice train track representative of it with some nice properties, and there's some criterion you can use to show if you have a nice graph representative satisfying certain properties, then it represents a fully reducible automorphism. So we verify that those properties are satisfied here.
So you can define Alexander polynomial also.
Yeah,
And that would be an element of the group ring,
that's right.
but I don't think you can say that the log discrete is real.
Is real analytic.
Yeah.
I agree, yeah, so there's some,
So there's more.
there's more to it, yeah. This particular polynomial has like certain nice properties. It comes from kind of a Perron-Frobenius matrix in this group ring, and that's what lets you say that you get this real analytic properties and so on. Yeah, so I'm slightly all that on.
Okay.
One comment. Stefan Friedl and I can provide you a Thurston ball for a surface order, for automorphism of any free group. Of course, we do not know this function, but I think there should be various things, interesting things going on.
I agree, and I would like to maybe talk to you about that.
Yeah.
Yeah, yeah, that seems like a very interesting thing, which confused me, so maybe you can explain it. I looked at the paper. Can I make one more comment that there was another group of people working on similar things, Echo Hironaka and Yael Algamfer and Kazarafni, and they also defined a polynomial like this and proved sort of similar theorems. So I just want to attribute that to them as well.
Okay, any more questions or comments? All right, thanks, Spencer.